Okay, so let's get started. So let me just start with an announcement. Assignment 1. Is due next Friday. Okay, so it's posted online. For the assignments, you should scan and upload on Moodle. Okay, and so we'll do 1 hour of lecturing today, and then we'll spend the second hour working on the assignment. I'll get you started on some of the problems so you know what to ask of you. Alright, so let's start with the summary of last time, where we started to introduce the techniques of the calculus of variations. We talked about virtual displacement. And that's basically displacement without the passage of time. And so virtual displacement we denoted as delta x. And that's different than the infinitesimal dx. So remember, if x maybe describes the position of some particle as a function of time, so x is a function of time, dx is how much x changes when time changes by an amount dt. Whereas delta x is a change in x that is without the passage of time. So the varied x is a different function than the original x. So dx brings you further along the function as a function of time, whereas delta x brings you to a new function. Okay. So we define the variation of a function by first introducing a varied function. Which we wrote f bar of x to be f of x, where x is now the dependent variable. Independent variable, sorry. Plus some small change to the function. So in this case here, so I'm sorry for mixing up t and x as the independent variable, because once we'll do all mechanics, t will be the independent variable. We care about functions of time. But in mathematics and calculus, people care about functions of x typically. So we'll mix the two. But we'll try to do most of the hardcore math stuff with x as the independent variable. Okay. So we introduce a varied function. So f bar is the function f of x plus some other function phi of x. And we have this epsilon in there that allows us to tune by how much we change f of x. And so we always care about when epsilon is small. So we can define the variation of f which we'll call delta f. And so that's f bar minus f. And so that's simply that small part that we added to f. So delta f would be epsilon phi of x. Okay. Well, then we saw several properties of this delta operator, and we found that it commuted with differentiation as well as with integration, and so those are properties that we'll use later. And then one property that I'll rewrite down again is the chain rule, which we'll use a lot. In fact, the assignment is mainly the application of the chain rule. So say we have a function y of x. So y is a function of x. And then we have capital F, which is a function of y. So capital F is really a function of y of x. So we saw, as a result of the chain rule, that the variation of capital F, delta F, is given by di F by di y delta y. And if f were, for example, a function of multiple functions of x, so let's say we have a y of x and the z of x and others, then delta f we would write as di f by di y delta y plus di f by di z delta z plus whatever else it would depend on. And in classical mechanics, or in analytic mechanics, we only need what we call the first variation. I.e., we only care about terms of order delta. So any term that's in delta squared, we'll say they go to 0. So this chain rule involves, if you remember, Taylor series expansion. And in that Taylor series expansion, we dropped the second order terms in delta. So that's most of what we need for the formalism of variations. We then showed we found that the stationary value of a function or the stationary point, I should say, of a function is given by requiring that delta f equals 0. So if f were a function of multiple variables, which we'll call q, q1 to qn, then we found that the variation given by the chain rule So sum of y equal 1 to n of di f by di qi delta qi. All right, so that's f depends on multiple functions q, and so the variation of f is that sum of di f by di qi delta qi. Right, that's what we just wrote on the previous page. But that sum must be equal to 0 for a stationary point in f. So a stationary point is if you think of f as a surface, it's a flat point on that surface, whether it's a minimum, a maximum, or an inflection point. And in this sum, so this sum has to equal to 0. The delta qi can be varied independently from each other. So what that means is, when I'm trying to find a flat point of the function f, I must be able to walk in any arbitrary direction, and the function should be flat in all of those directions over an infinitesimal distance. So that means that I can go in any direction. So that means that I can choose any delta q, and so the delta q1 is independent of the delta q3. So if I want to move along the x-axis in a certain direction, I can also move around the z-axis in some other arbitrary direction. The two are uncorrelated. Okay? So that's what I mean when I say the delta qi can be varied independently from each other. That means that in this sum, the delta qi are independent. So in this sum, each term must be 0. And so for each term to be 0, we find that di f by di qi equals 0. And that's the condition for a stationary point. And of course, that's the result that you would expect from calculus. Now, if we have a constraint, the delta qi cannot be varied independently from each other. So for example, we might have a function lowercase f of the q's equal to 0. And that would be what we call our constraint equation. So now that you have this additional constraint equation, so an equation that relates the q to each other, then you can always write one of the q's as a function of the other q's. And so the delta of that q depends on all the other delta q's. And so you can't just vary them independently. So that means that the individual terms in the sum cannot all be 0. And so if that's the case, we can use a method that's been introduced by Lagrange called the Lagrange multiplier. So it's called the method of Lagrange multipliers. And so how that works is you build a new function let's call it f bar, and that'll be given by our original f, capital F, plus lambda lowercase f. And then the stationary points of capital F subject to the constraint lowercase f, those stationary points are given by the condition that di f bar by di qi equals 0. So that's an equation with lambda in it. And then the second equation that you need to solve is that the f of the q's equal to 0. So that will be n plus 1 equations that you need to get lambda. So any questions about that material? It's rather formal without an example, so let's do an example. So this is example 2-3 in the notes. So we want the dimensions of a box we want x, y, and z for a box that maximizes the volume of the box for fixed surface area so the area of the box has to be 2 times A. Okay, so basically the problem is you have a sheet of cardboard of surface 2A, and what is the box with the largest volume that you can build with that amount of cardboard? Okay. So since we want to maximize the volume, we want to maximize the volume, which I'll call F, and that's given by x times y times z. That's the volume of the box. And it's subject to the constraints and the constraint is that the area of the box is equal to 2A. So the area of the box has 6 faces, right? So it's a closed box. So the area of the box will be 2xy plus 2yz plus 2xz, right? Each face, there's an xy face, a yz face, and an xz face, and there's 2 of each faces. And so that area has to be constrained to be equal to 2A. So in other words, this minus 2A equals 0. And so I can call this little f. So little f is the function 2xy plus 2yz plus 2xz minus 2a. And so the constraint, we can write it in the form of little f equals 0. Okay, so now we use our method of Lagrange multipliers to solve this problem. So to use the method of Lagrange multipliers, we build a new function f bar that's given by f, so x, y, z, minus lambda times, or plus lambda, I guess we've been using, plus lambda times little f. So little f is 2xy plus 2yz plus 2xz minus 2a. So now the stationary point of capital F, given the constraint lowercase f, is found by setting all the partial derivatives of f bar to 0. So f bar is a function of x, y, and z, and then it also depends on lambda. So the condition that di f bar by di qi equals 0, in this case, gives us 3 equations. So first we have di f bar by di x, that's got to equal 0. So di f bar by di x, the first term has an x, so that's yz, plus lambda, and then the terms with x's in them, there's a 2y and 2z. Sorry. I just realized the whole point of putting 2a in the beginning was so that the 2's would all cancel at the top here. Let me do that. Since this is all equal to 0. And then I'll erase all the 2's here. Okay, so hopefully that doesn't confuse anybody. I apologize. Okay, so that's one equation, that's got to equal to 0. To do the other ones, we have di f bar by di y. So that's going to be equal to xz plus lambda times x plus z. And that's got to equal 0. Then we have di f bar by di z. That's equal to xy plus lambda times x plus y. And that's got to equal to 0. Right, so that's the condition for f bar to be stationary. And that means that f will be stationary subject to lowercase f. So this gives us 3 equations, 4 unknowns, right? The 4 unknowns are x, y, z, and lambda. But the 4th equation is the constraint equation. Oops, what happened here? Sorry for that. So the 4th equation that we get is the original constraint equation, which is xy plus yz plus xz minus a equals 0. So that's 4 equations, 4 unknowns. The unknowns are x, y, z, and lambda. Alright, so now it's just math. Well, I guess it's math the whole time. It's very boring math. So we can solve these equations. You'll note that if you multiply the equations by x, y, and z simultaneously, or I multiply the first one times x, the second one times y, and the third one times z, then each of the equations has an xyz term in them. Right? So if I multiply the first equation, I have xyz plus lambda x times y plus z. The second equation will be yxz plus lambda y times x plus z, etc. So all equations will have an xyz term in them. And so let's take, say, the first two. Well, let me just write them out. It'll take our time. It's hard for me to gauge, like, if I'm going too fast or too slow with the math. So let's just go slow. And let's write down the 3 equations now once they've been multiplied. So the first equation becomes xyz plus lambda x times y plus z equals 0. The second equation is xyz plus lambda y x plus z equals 0. And the third equation is xyz plus lambda z x plus y equals 0. Okay? So let me take now the first 2 equations. And set the xyz terms equal to each other. So that gives me lambda x times y plus z equals lambda y times x plus z. Right, so in both cases, so there's a lambda xy on both sides, right? So that lambda xy cancels, so then I have lambda xz equals lambda yz, and the z's cancel. So I have lambda x equals lambda y. So I realize the lambdas cancel, but we have 2 possibilities here. The first option is that lambda equals 0. And the second option is that x equals to y. So let's think about these 2 options. So if lambda is equal to 0, right, I can't divide the lambda out. So if lambda is equal to 0, let's go back up to the first equation. So if I rewrite the first equation with lambda equal to 0, then I find that xyz must also equal to 0. So if xyz is equal to 0, then the volume is equal to 0. So we're trying to find the dimensions xyz that maximize the volume. And so we found a solution where we in fact minimize the volume. Clearly 0 is the minimum volume. But that makes sense, right? Because all we've done so far is to use the condition for finding a stationary point of our function capital F. and the minimum is a stationary point. So we've in fact found one of the stationary points, just not the one we care about. But that's okay. We can think about it and reject that point. The reason we have to think about it is because we're only considering the first order variations, so we never calculated, say, the second order derivatives to find out the curvature of that particular stationary point. So it shouldn't be that surprising that we end up finding a point that's not necessarily the one we cared about. The second option is x equals y. And then, you could solve the last two equations just like we did for the first two, and then you'll find that that's also equal to z. Right, so you find that x, y, and z are equal to each other. And so when x, y, and z are equal to each other, we call that a cube. So it appears that shape of a box that maximizes the volume for a given area is actually a cube. And maybe you expected that. So we haven't quite finished the problem, right? So we know it's a cube, so now we have to find out what x, y, and z really are equal to. So we've used up the three equations that we had from the stationary point, but we still don't know what lambda is. So we have our fourth equation. So we use our fourth equation to figure out the dimensions of the cube. So now we use the constraint equation, which was x, a function of x, y, and z equals 0, to solve for x, y, and z. So the function f was equal to xy plus yz plus xz minus a. Right, and so that constraint equation must equal to 0. So now we have x, y, and z are all equal to each other, right? So that's like saying 3 times x squared equals a, or x equals square root of a over 3. And now we've solved the problem, right? So we know it's going to be a cube of size square root a over 3. And in this particular problem, we actually never needed to solve for lambda. That's not always true. So sometimes you will have to solve for lambda, but in this case we did not. So any questions about this problem? This is something you may have covered in undergraduate calculus, because it doesn't strictly require variations. We just used it as a method of variational calculus. Okay. So if there's no questions, let's continue. So far we've looked at minimizing a function, so finding a stationary value of a function rather, subject to a single constraint. So what about the case when there are multiple constraints? So we still want to find stationary values of a function capital F that depends on q subfunctions, n functions q, so q1 to qn, subject to, let's say, k constraint equations. All right, so it's like the problem that we just did. Let's say, the volume of the box needs to be maximized. The total area of the box is 2A, but you need one dimension of the box to be equal to a specific number. So there you have an additional constraint. So how do you handle that additional constraint? So the answer hopefully will become obvious is you have to use multiple Lagrange multipliers. So let's look at that. So let's say we have k constraint equations. So we're going to label the k constraint equations as f1 of the q's. That's the first constraint equation. Then we'll have f2 of the q's equals 0 all the way to fk of the q's. So these are our k constraint equations. So this means we have, in principle, we have n minus k, what we call degrees of freedom. So we could use these k equations to eliminate k of the q's and have the initial function as a function of only n minus k variables. But then we run into this problem of which q's should we eliminate, and isn't that choice arbitrary? And then we start treating some q's differently than others. So we would rather avoid that if possible. And maybe we want to keep all of them, actually. Okay, so the way to do that is, again, with the method of Lagrange multipliers. So because each of these f's is equal to 0, the delta f's is also going to be equal to 0. So if we consider the variations of these fi, we have delta fi. So you can write this for f1, f2, and all the way up to fk. So delta fi of the qi's, so q1 to qn, is equal to 0. And remember that delta fi, using the chain rule, we can write as the sum from I equals 1 to n of di fi. Oops, that should not be an I. Let's use j here. Delta fj is di fj by di qi delta qi. So I'm going to make that a j up there. Okay, so j is any number from 1 to k for the our constraint equations. And then I, in this case, is the sum over all the different q's. That goes from 1 to n. So we have that all of the delta f's must be equal to 0, lowercase. And then we also have delta capital F, which remember was the sum from I equals 1 to n of di capital F by di qi delta qi. That must also equal to 0. So there's no reason that I can't build a function that's 0 plus 0, and that's still going to be equal to 0. So let me construct delta f plus lambda 1 delta lowercase f1 plus lambda 2 delta lowercase f2 plus all the way to lambda k delta fk. That has to be equal to 0. So we introduced here k Lagrange multipliers. This linear combination of the delta f's, where the lowercase f's are multiplied by these arbitrary lambda multipliers, since all the deltas are 0, then this equation is true. So I can write this equation using the chain rule. So I have the sum from I equals 1 to n. So the delta f term is going to have a die capital F by die qi. I'm going to factor out the delta qi since the lowercase f's also have delta qi's in them. So this linear combination I can write as a sum from I equals 1 to n of die capital F by die qi plus lambda 1 die lowercase f1 die qi plus lambda 2 die lowercase f2 by die qi all the way to lambda k die fk by die qi. And that all multiplies delta qi, and the whole sum is equal to 0. Okay? Everything okay so far? So now we come to the point where we can choose the values of our Lagrange multipliers. Okay? Let me go to a new page. So let me make it, a comment again here. So we have this sum here, right? So it's each term in the sum multiplies a delta qi, right? So in the case where there was no constraints, you don't have any of the lambda terms, the delta qi's can be varied independently from each other, and so that means each term in the sum must be equal to 0, independent of delta qi, and so that gives us the condition that die f by die qi, die capital F by die qi, is 0. So if you don't have any lambdas in there, and the delta qi are independent from each other, only the first term survives, and each of those first terms is equal to 0. So die capital F by die q1 is 0, die capital F by die q2 is 0, etc. Which is what we just did for the example with the box, right? In this case with the constraint, you now have, you're not allowed to vary the delta q's independently. You can't walk in any direction along the surface to find the flat point because there's a constraint. So maybe there's a wall along the surface. That's what the constraint equations are like. Okay, so the terms are not each equal to 0 because the delta qi's are not independent. Now we threw in these arbitrary values lambda, these Lagrange multipliers, and there's k of them. So that means we can make k choices for those multipliers. And so we're going to choose those multipliers. So we choose lambda 1 lambda 2 all the way to lambda k, such that the last k terms in the sum are equal to 0. So let me write the last term in the sum. So the last term in the sum, that's the nth term, right? The sum goes from I equals 1 to n. So the nth term in the sum is di capital F by di qn plus lambda 1 di lowercase f1 by di qn plus lambda 2 di lowercase f2 by di qn plus etc. di fk by di qn equals to 0. That's the nth term, right? So it's the last k terms. I'm choosing the lambda so that the lambdas, sorry, I forgot the lambda in the last term. I'm choosing the lambda so that the last k terms in the sum are equal to 0. So the last term is this. The second last term is the n minus 1 term. So that's going to look very much the same. So that's di f by di qn minus 1 plus lambda 1 di lowercase f1 by di qn minus 1 plus etc. lambda k di fk by di qn minus 1 equal to 0. So since it's the last k terms, so the last term is n, so the second last is n minus 1. So the first of the last k terms is the n minus k plus 1 term. So that means that di capital F by di q n minus k plus 1 plus lambda 1 di lowercase f1 by di q n minus k plus 1. So it's lambda 1 plus lambda k di fk by di q n minus k plus 1 equals 0. So that's the last k terms. So the last k terms in the sum are all 0. So let me rewrite the sum now without the last k terms, since the last k terms are all 0. So the sum becomes the sum from I equals 1 to n minus k di f by di qi plus lambda 1 by lowercase f1 by di qi plus all the way to lambda k di f k by di qi delta qi. And so that's still equal to 0. Now, this sum equals to 0 only has n minus k terms. So effectively now the delta qi, there's only n minus k of them, which is the number that we were treated of. So they can all be treated now as independent because there's less of them. And there's in fact exactly the right number, the minimum number of independent ones. Alright? So in this reduced sum, the delta qi's can be varied independently. So we only have n minus k delta QIs. These can be varied independently. So if the delta QIs can be varied independently, that means that each term in parentheses must be identically zero, because it must be zero regardless of the choice of delta QI. So since that's true, well, since every term in the sum must be zero, then we get for I going from 1 to n minus k, so only for the terms in this sum, we have that di f by di qi plus lambda 1 di lowercase f1 by di qi all the way to lambda k di fk by di qi equal to 0. So we have n minus k such equations. Right? So this is true for Q1, Q2, all the way up to Qn, right? So let's look at now our equations that we have. So up here, we have for the terms Q that go from n minus k plus 1 all the way to n, so the last k terms, we have these equations. And they all have di capital F by di qi plus lambda 1 di f by di qi, lambda k di fk by di qi equal to 0, right? And then those are true only for I equals n minus k plus 1 to n. And then we took those, put them in the sum, removed those terms from the sum, and then we got the equivalent terms for I equals 1 to n minus k, so for the first n minus k terms. Of course, when you compare the two equations, they're identical. And that's the whole beauty, of course, of the Lagrange multiplier, is that it doesn't make a real distinction between the terms you're eliminating and the terms you're keeping, because in the end you get the same equations. And so the conclusion is that for all I, you end up getting di capital F by di qi plus lambda 1 di lowercase f1 by di qi plus etc. lambda k di fk by di qi equal to 0. So the Lagrange multiplier method, it tricks you into thinking you're treating the last k variables in a special way by eliminating them, but then you end up finding that the condition to eliminate those variables, the last k variables, is the same condition as the first n minus k variables. And so in fact, they're all treated symmetrically. So thus we find that we can build a new function which we'll call capital F bar, which will also depend on the Q's, and it will be given by the original F, and then plus lambda 1 f1 plus lambda 2 f2 all the way to lambda k fk. And then the stationary points are found by requiring, on the one hand, that the die F bars by die Qi equal to 0. That'll give us n equations, right, because there's n different Qs. And then we also have that the Fj's equal to 0. And you'll have k such equations. And that's good. So you have n plus k equations, and you have n plus k unknowns, right? You have the n values of the q's that define the stationary point, plus the k unknown Lagrange multipliers. Okay? Any questions about that? Okay, so this is a good starting point lecture-wise. So let's move on to assignment 1. So if you go to the Moodle site, let me go to the Moodle site, and you go to the section for this week, there's 2 things. One is assignment 1, and assignment 1 tells you to do 3 problems, and those 3 problems can be found in the other attachments to this week's section, and I think it's called like chapter introduction problems or something like that, or chapter 1 problems. Alright, so there's a list of problems that roughly cover issues of chapter 1. And so I've asked you to do 3 of these problems, problem 1-1, problem 1-2, and then problem 1-7. Problem 1-7 will require a computer, presumably. Well, for sure, because you have to make a plot. So I'm going to give you 5 to 10 minutes to read those problems, and then what I'll do, if they sound obscure, I'll do part A of problem 1-1 and part A of problem 1-2, so that you see what they're asking for. Some of them actually involve quite a lot of math. Well, a lot of taking derivatives in the chain rule. So let me you get started on that, and maybe in 5 minutes I'll start working on problem 1-1A for you guys. And then I'll give you some time, and then I'll do problem 1-2A. So again, the assignments are not mandatory, right? If you don't hand in assignments on time, you can choose to have the final exam worth 75% of your marks. That may or may not be risky for you. That's up to you to choose. The assignment is due next Friday. So maybe let me also introduce Michelle, who just joined the session. Michelle is a PhD student from USB, but she's based out west near Surf. And she will be the marker for the class, and she will help to run these tutorials in the future. So for now, I just asked her to join so that she could see what it would be like. So Michelle, I've asked the students to go on to Moodle, and on Moodle they can find assignment 1, which lists 3 questions that they should do from the problem sheet. And I've asked them to start looking at those questions, and in 5 minutes I'll start helping them with, I'll do part A of the first 2 questions. So that's the idea.
Okay, that sounds good. I will take a look at them as well.
Good. Okay. So let me have a crack at problem 1.1, part A, in case it wasn't super clear what you're asked to do. So in problem 1.1, you're given a bunch of coordinate transformations. Where on the left-hand side would be your usual Cartesian coordinates, and they have maybe an indice like an index like x1, y1, z1. So think of a system with many particles, and you want to describe the position of each particle. So each particle maybe is a particle I, and so each particle has an xi, a yi, and a zi. And so that would be describing the system in Cartesian coordinates. But then maybe there are constraints and whatnot, and then you find that there are a better set of coordinates q, so-called generalized coordinates, and maybe there's less of them, that are more practical for describing the system. And so you must be able to have transformations to describe the system using either one set of coordinates or the other. So in this problem here, I give you these transformations between the Cartesian coordinates on the left and the generalized coordinates, which I've labeled q, on the right. And so the question asks you to find the velocities of the Cartesian coordinates as expressed in the generalized coordinates as well as the acceleration. That's something that we actually did in the example with the compound pendulum. All right, so let me do 1.1a. So the transformation equations that we have are x1 equals L, which is the constant, times cos of our generalized coordinate q1. So in this case, q1 is some sort of angle, presumably. We have y1 given by L sine of q1, and then we have z1 given by simply q2. So remember, these are the coordinates of particles. So x1 is really a function of time, right? And similarly, q1 is also a function of time. So I just don't write the t's everywhere, but the coordinates should always be thought of as functions of time. So let me find out three Cartesian velocities, and then we'll do the three Cartesian accelerations. So the Cartesian velocity, so the rate of change of x1 with respect to t. So what we want is x1 dot. Remember, that means dx1 by dt. So if I do d by dt of L times cosine of q1, then L is a constant, so I have L times d by dt of cos of q1. Remember now, q1 is a function of time, so it's cosine of a function of time, so it's the chain rule. So that's L times the derivative of cosine, which is minus sine. And then it's times the derivative of what's inside, right? So then it's dq1 by dt. And to use our preferred notation, we'll write this as L as minus L sine q1, q1 dot. Any questions about that? Alright, so now let's do y1 dot. So y1 dot is going to be, by the same thing, it's going to be L cosine of q1 dot, right? L is a constant, so derivative of sine is cos, and then the derivative of what's inside is q1 dot. And then z1 dot, so that's d by dt, if z1 is equal to q2, so it's just going to be q2 dot. So that's the first thing that you're asked, is to find the 3 Cartesian velocities expressed in terms of the velocities of the generalized coordinates. And the second part is to do the same thing with the accelerations. So for the accelerations, we want x1 double dot, right? So that's d squared x by dt. So that's going to be d by dt of what we had minus L sine of q1 dot, right? So again, the L is a constant. So now it's the product rule, right? And the chain rule. So it's d by dt of sine of q1 times q1 dot. So it's like d by dx of f times g is f prime g plus f g prime. All right, so that's going to be equal to, if I first take the derivative of sine q1, so the derivative of sine q1 is cos q1 dot, right? d by dt of sine q1 is, from the chain rule, cos q1 dot, and then I have to multiply this by the q1 dot that I already have. So it's q1 dot squared. And then the other term is plus sine of q1, so that's unchanged. And then it's d by dt of q1 dot. And so d by dt of q1 dot is q1 double dot. So that's the answer for the x Cartesian acceleration. Similarly, y1 double dot is going to be equal to L times, so then we have cos of q1 times q1 dot. So the derivative of cos of q1 is minus sine q1 dot, and that's got to multiply q1 dot, so there's a q1 dot squared. And then the second term is plus cos of q1, and then we have a q1 double dot. And so that's the end of part A. So if you look at, for example, part B, it's the same thing, but everything's multiplied by q2.
You want to do z as
even
well.
when you take the
You want to do z dot as well.
yes, that's true. I do want to do z dot. So z1 double dot is going to be q2 double dot. Sorry. Thanks for pointing that out, Michelle. Okay. So that's the end of part 1. So like I was saying, part B, even when you take just the velocities, just for x1 dot, right, you already have to do the product rule and the chain rule because you have the cos q1 and q2. So both q's are, of course, functions of time. And so you're going to end up with 4 terms once you've done the acceleration, etc. All right, so let me give you maybe until hour working on this problem, and then I'll do problem 1, 2, part A. Of course, if you have questions as you're going, please let me know. I've assumed that, for example, you're going to need to know the derivative of arc tan, the inverse tan. I assume since you're clearly on a computer that you can just Google that. Yeah. All right. So nobody having any issues? At least the problem 1-1. I'll point out that you can always ask questions. One is like the little hand button in underneath your name in Blackboard. So if you press that, it's like raising your hand and it makes a ding sound and catch my attention. You can type your questions into the chat box, or you obviously can use the audio, and then you have to press the talk button. All right, so let me maybe get started on part A of 1-2. So in problem 1-2, it's basically how do you arrive at problem 1-1. So I give you how many? A, B, C, D. So 4 different physical situations that are comprised of multiple point particles, and you're asked to specify how many degrees of freedom there are, suggest that many generalized coordinates, and then write out the kinetic energy of the system in terms of those generalized coordinates. So in all cases, the system is 2-dimensional, so it's constrained to the plane of the page. And for parts B, C, and D, there are figures that go with it. Okay. So let's do part A, which we somewhat started in the notes as well. So that's the case of 2 masses. They're both equal, and they're connected by a massless rigid rod. So here are 2 masses. I guess I forgot to specify in the question the length of the massless rigid rod. But let's take that as given, and I'll update the question, and let's say it's equal to L. So the first question, the first part is how many degrees of freedom are there? So there's 2 particles in 2-dimensional space. So that's 2 times 2, so there's 4 possible degrees of freedom. But we know because the 2 particles are constrained to always be a distance L from each other, that we can get one constraint equation from that. And so the number of degrees of freedom is 3. So we have 3 degrees of freedom. So we must now choose 3 possible coordinates to describe the system. So this is up to you. But here's my choice. So let's choose x1, y1, and theta. So what do I mean? So let's say that this is particle 1 and particle 2. So x1 and y1 are the x and y positions of particle 1. And then theta, I'm going to introduce an angle here to be the angle that the rod makes with the x-axis. Magic of the computer. Let's make sure to specify that we have an origin. Okay. So x1, y1, are the position of the first mass. And then theta is the angle. So that's what we're going to use as our 3 degrees of freedom. Okay? So we need to know the transformations from our Cartesian coordinates to our generalized coordinates. So we have 4 Cartesian coordinates, right? We have x1, y1, x2, and y2. Well, let's write out x2 and y2 up here. x2 and y2. So we need to write out equations for x1, y1, x2, y2 in terms of x1, y1, and theta. All right, so the transformation equations well, for x1 it's trivial because x1 is x1. y1 similarly. x2, so if we look at our diagram, x2 is equal to x1 plus L cos theta. Right? And then y2 is y1 plus L sine theta. So we have our transformation equations. So now let's find our velocities. So the x1 dot, so the left-hand side dot as a function of the right-hand side. So of course x1 dot is trivial, it's just x1 dot. y1 dot is trivial, it's just y1 dot. Then we have x2 dot. So that's d by dt of x1 plus L cos theta. So d by dt of x1 is just x1 dot. And then d by dt of L cos theta, in fact we did that earlier, that's minus L sine theta, theta dot. Similarly, y2 dot is going to be y1 dot plus the derivative of L sine theta, which is L cos theta, theta dot. Okay? Remember, the question here is to specify the kinetic energy of this system using the generalized coordinates. So the kinetic energy of the system, we're going to use always the letter T for kinetic energy in this course, capital T. So the kinetic energy T, so it's the kinetic energy of the first particle plus the kinetic energy of the second particle. So the kinetic energy of the first particle is a half m, and then d squared is x1 dot squared plus y1 dot squared. Right? The square of the velocity is the square of the sum of the components. So the kinetic energy of the first particle is a half m x1 dot squared plus y1 dot squared. Similarly for the second particle, it's a half m x2 dot squared plus y2 dot squared. So now you can see why we wanted to know x1, y1, x2, y2 dot as a function of the generalized coordinates, because now we can plug them into the equation for the kinetic energy. Okay, so now it's just a matter of math. Tedious math, usually at this point. So we have a half m, that's in all the terms, then from the first particle we have x1 dot squared plus y1 dot squared plus, now x2 dot squared, I'm going to use what I have up here. Alright, so x2 dot squared is x1 dot minus L sine theta theta dot all squared. So if I square all of that, I get x1 dot squared minus 2 x1 dot L sine theta theta dot, and then plus L squared sine squared theta theta dot squared. And then plus y2 dot squared, same thing, I get plus y1 dot squared plus 2y1 dot L cos theta theta dot plus L squared cos squared theta theta dot squared. This simplifies a little bit. This is often the case when you have a x and y given by L cos theta and an L sine theta. So let's simplify. So we have half m. So the x1 dot squareds, there's two of them. So there's 2 x1 dot squareds. There's 2 y1 dot squareds. Now let me underline the last terms in red here. So if I add these two terms together, L squared sine squared theta dot squared plus L squared cos squared theta dot squared, I can factor out L squared theta dot squared. Right, so it's L squared theta dot squared times sine squared theta plus cos squared theta, which is 1. Right, so those whole terms, when you sum them together, you get L squared theta dot squared. Now, unfortunately, the cross terms, the ones that mix x dots and theta dots, does not anything pretty you can do with them. So let's just factor out 2L theta dot. So we have plus 2L theta dot. And then we have y1 dot cos theta minus x1 dot sine theta. And that's the answer. That's the kinetic energy expressed in terms of our generalized coordinates and the generalized velocity. And so it turns out the kinetic energy is always very easy to write in terms of Cartesian coordinates. So it's often true that we start by writing the transformations from the Cartesian coordinates to the generalized coordinates, and then do the kinetic energy. Because in Cartesian coordinates, the kinetic energy is just the sum over the x, y, and z dot squared. Okay, so then for the rest of this problem, it's the same thing. You have to figure out the number of degrees of freedom, figure out a good choice of generalized coordinates that's equal in number to the number of degrees of freedom, and then finally write out the kinetic energy. I warn you that part B, the 4 masses connected by 4 masses rods, gets really involved mathematically. It's easy, but the terms become large because you have to square them, right, when you do the kinetic energy, and it becomes a bit of a mess. So I'm fine if you want to outline how to do it and then solve it with a computer, using Maple or whatever. That's acceptable. I'm not testing your math skills. I want you to do the math correctly, but I don't care if you have to write. The goal is not to make you write 3 pages of derivation. The goal is to make you understand what you're supposed to do. Let me also make a comment. Well, actually, is there any questions about problem 1, 2? You have to be a little bit more creative because you have to choose the degrees of freedom yourself. Okay, let me make a comment about problem 1.7. So for problem 1.7, which is those two masses that are connected by springs, you have to find the number of degrees of freedom. Then you have to choose, suitable generalized coordinates that match the number of degrees of freedom. And then in part B, I ask you to write out the differential equations of motion. So when I say write out the differential equations of motion, so let's say you called one of your generalized coordinates Q. So the equation of motion would be, Q dot equals something, or Q double dot equals something. So presumably here you're going to have to use Newton's second law to figure out the equations of motion, and you'll end up, if you're using Newton's second law, then you're using F equals ma, and ma, remember, is going to be one of the variables double dot. So you're going to have Q double dot equal, whatever the forces are from those springs. Okay, and then the last step is to, I give you specific numbers, and you have to plot the motion of the bottom mass as a function of time. So that's all I wanted. That's all I wanted to cover today. Are there any questions? Okay, so did you? Yes, so I did use that equation, right? So the two things that I'll point out is that in problem 1.2, I specified that it's in two-dimensional space. So we start off in a two-dimensional space, so it would be 2m plus 3m minus h. And then the m was 0 because there's no rigid bodies, so then it was 2n minus h. And so for the part A, where n is 2, so it's 2 times 2 minus h, and h is 1 because there's one constraint, so then we end up with 3 degrees of freedom. Okay? So the 3 in 3n is because there's 3 Cartesian coordinates. Okay, so this is due on next Friday evening if you want to hand it in to be marked, which I suggest. Okay, so if there's no more questions, that'll be it for today. Thank you, everyone.